Now let's do the same thing for a second order reaction. And again, I'm going to simplify it big time. I'm just going to say we got one reactant going to things, but this is actually a second order reaction. So the rate law will be rate equals K times the concentration of A squared. So the units of K, let's figure that one out. The units of rate, moles over litre time. K we don't know. Concentration, moles per litre, but we got squared, so it's moles per litre times moles per litre. Moles per litre cancels out from the left-hand side and one of the right-hand sides. So now K over here, we're going to have units of K will have time on the bottom to match up to this side. But we've got to get rid of a moles over litres here, so we have to put a litres over moles for K. So K is going to be litres over moles to cancel this out, and whatever your time units are here. So some examples: litres per mole second, litre per mole s, 1 over molar second, blah, 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 blah. All various ways you can do it. Now, although I'm not going to dwell on it, if we did a third order, we'd still have time on the bottom, but now it would be molar to the -2. So it'd be litres squared over mole squared. Fourth order would be litres cubed over mole cubed, and so on. And there's a couple of questions associated with that on the main quizzes. Not sure how people will do on that before we've had this conversation, but anyway, now let's do the integrated rate law. So again, rate is K times A squared. Rate is minus change in A over change T equals KA squared. Do this infinitesimally, so we get minus d over dt equals KA squared. Rearrange it a little bit and put the integral signs in. So I have the minus dA on this side, bring the A squared down to the bottom, take the dt up to the top, make sure you see that. And now the integral of 1 over A squared is A to the -2 will be 1 over A to the -1 times -1. So that just becomes 1 over A, because we had -1 over A and we had that minus sign there. Integral of K with respect to T, KT plus C. Again, if T is 0, A is A0, so this goes out. A is A0, so C is equal to 1 over A0. Pop that in and rearrange it a little bit, and we get the nice integrated rate law for a second order reaction. 1 over the concentration, minus 1 over the initial concentration equals KT. Again, I hope you can see we've got concentration on one side, we've got T on another. So let's go to the same considerations. There's our nice little drawing of concentration of A against time as time goes ahead. Start off with the initial concentration of A, but now this graph, which looks very much the same, has a different relationship. It's no longer an exponential graph, it is a reciprocal graph. But it's still, here is the equation of this graph. You've got concentration of A, you've got T. Let's make it nice again. Just rearrange it ever so slightly into that Y. 1 over A is mx, K is constant m, T is like x, and here is the other constant, 1 over A0. Plot everything out. The animation is going to be the same because I had fun doing it, so we might as well do it again. So now instead of just a generic x and y, let's plot 1 over A against time, and I hope you can see this matches up to the straight line equation. B, the intercept, is 1 over A0, and the slope is simply equal here to K. Thus, if a reaction is second order, you don't get a straight line by plotting log of A, you get a straight line by plotting 1 over the concentration of A against T, and that slope, instead of it being minus K, is a straightforward K. Integrated rate laws, very, very important concept. Show you how you can determine K for first order, for second order reactions by plotting the appropriate function of the concentration against time. If it's a first order reaction or a pseudo first order reaction, plot the natural log of the concentration against time. The slope is minus K. If it's a second order reaction, plotting 1 over the concentration against time gives you a beautiful straight line for which the slope is plus